All right. So I'm going to talk a little bit about what I did in the last years and show you where my little nudge forward from that. This is what we're taught to do for risk assessment in cybersecurity. So step one on the left side of it is a spreadsheet where you list ways that hackers can steal your data. Step two is on the right side of the table, you rate each of those scenarios by how probable they are. And then step three is you rate each of those scenarios by how bad they could be for us if they did occur. Step four is you multiply the probability and the impact ratings together, and you get a risk score. So that's it. Your risk has been assessed. And now you should pay for cybersecurity. That's usually how the conversation goes from cybersecurity consultants. And basically, it's a 5-star rating system, but then they multiply the stars together, which so far, not even dubious marketing firms have tried yet. So if you, just as an example, if you take the probability that a malicious email attachment will be the case, or a data breach will result from a malicious email attachment over the next 12 months, I give it 2 stars as a probability. This is what they actually do. Then what is the potential impact of an email? The potential impact of an email resulting in a data breach, you might give it 4 stars because maybe that email account is an executive or something. So then the risk analyst multiplies those 2-star ratings together. The magnitude of badness is multiplied by the probability of badness. So this is what regulators have lowered their standards to because people have a hard time adopting anything more sophisticated than this. So if you ask people if to use dollar amounts, their management gets nervous about having this very clear risk on paper, and they tend to question it a lot more once you start using real numbers. And then if you ask people to use percentages, they have radically different definitions of what 10% means compared to 20%. So the best that is recommended and that you have is that you have to memorize. Sorry. So the best that is recommended and that you have to memorize in order to get security industry certifications is the Dubious scoring method. And your job as a security professional becomes lowering the score. So when management is inevitably confused by these scores or stars, we're taught to present the risks with a traffic light colored heat map that dazzles management with pretty colors. And we say, fear not, my security will reduce your cybersecurity risk from high to medium. And many problems arise from this methodology, as you can imagine. I'm not going to get into those here. If you did want to learn more about that, follow my social media channels. There's free talks on judgment and decision-making psychology and expert knowledge elicitation at hivesystems.io, where we talk about, where I try to take the science and apply it in the industry. So again, this is our primordial risk assessment that the industry is started with. And again, when you do a certification in cybersecurity, you have to memorize how to do this, even though I personally think it's very wrong. And to move into BayesiaLab, one way we attempt to improve this is to have the high, medium, and low 3-bucket domain, and then use deterministic connections, such as a high probability and a high impact equals a high severity risk, or a low probability and a high impact rating equals a medium risk, etc. That's kind of the next step. But that still makes me uncomfortable because it still scores. And this also uses those highly subjective ordinal words like medium and high. And it's still unrealistic because it's this compressed domain where a rating of high could mean $100 as a result of a data breach, or a data breach fines, or a rating of high could mean $11 million. So introducing dollar amounts and percentages as continuous variables does help us some. It gives us something less sensitive to the varying subjective understanding of words like high, medium, low. The issue still remains that a high consists of any risks with losses greater than 100,000. In cybersecurity, the domain of potential loss varies extremely, and oftentimes suddenly. So if you review public data breach loss amounts, you'll find situations where massive sensitive data sets are breached and cost a company hundreds of thousands of dollars. And that's for this big data sets show about in the news. But then you'll also see losses due to a single stolen laptop that an employee left in a cab. It's unencrypted, and it contains significantly less data about significantly fewer people, but the type of data in the spreadsheet is so much more sensitive and it upsets just the right people that it results in tens of millions of dollars in losses. So for that reason, discretization can be hazardous for us when assessing risk in the domain. So all of these issues assume you have a fairly good idea of the potential losses. There's also the elephant node in the room that is not represented with this model, and it's uncertainty. So this approach doesn't allow the expert to express uncertainty and where it's and what it would look like given these that they only have three options. Researchers have demonstrated success with the use of range estimates. So if you ask your expert to provide a ballpark estimate and then have them narrow it down some, but not down to a single number, that is, you keep the range, that is shown to allow them to express their uncertainty, give better, higher quality decisions in the long run. Basically, don't let humans converge. They converge poorly, so only let them come down. Don't let them use single numbers when they're giving an estimate. And we can collect ranges for probability as well as impact estimates. So, for example, suppose you're an engineer and suppose your engineer, your IT department, or Amazon Cloud says that the cost of replacing a particular server due to ransomware could be as little as $1,000 or as much as $100,000, but most of the time it's about $4,000. So that's a range estimate. And that range might be because the context that you're asking them in is that there's nothing too sensitive on this server, but it costs us. There's an outage. Facebook and its services were all out for a long time. In that case, they're claiming that it was not a security incident, but if it was, there's still money lost just by having the system down, especially for companies like that. And we can do ranges in BayesiaLab. So one way is by adding hyperparameters with function nodes. Another way is Beaky. Another way is shift clicking and manually shaping your distribution. And shown above is an example of how that can be done. The green function nodes are showing your user input. And then the distribution shapes are the results of your probability table being populated with a distribution shape by those parameters that you entered. So you have a formula in the background taking into account those parameters. It could be triangular, for example, for a simple example, or beta. So you have one node set for the probability estimates, then you have another for the impact estimates. And you can use the outputs of those distributions as the inputs for your risk estimate, your product. So if the distribution is populated and visualized on the long horizontal table on the right side here, and that final rightmost probability table is populated by your probability impact estimates as well as your experts expressed uncertainty, unlike the previous approach with the three buckets. If the expert is calibrated, their estimates can be reliable. And if the expert is not calibrated to provide estimates, we still externalize their mental model for peer scrutiny and ongoing refinement. In BayesiaLab, the risk scenarios are the qualitative verbal part of your evidence scenarios. So for each risk scenario, that is the thing that we're worried about happening in cybersecurity. And as a side note, when people want to consider combinatorial scenarios or cascades of loss events occurring, they just create a new row in the tradition of risk assessment, a new row that just has a much longer description where the chain reaction is spelled out in a single row. And there are, of course, great ways to model that interaction and co-occurrence more fully in BayesiaLab. But just to try to stay close to what people are used to, that's the approach that I've been taking. And I'll present those either at the next BayesiaLab conference or in one of my video streams. Again, it's hypesystems.io, where I'll follow up on these. The next step in a risk assessment is to propose security controls and then repeat the estimation process but factoring in those controls. So those are your conditional, those are your conditions. And so what's the risk now, given that you have a firewall in place, antivirus in place, and so on. So that enables people to select which security controls are most effective, as well as which controls give them the biggest bang for their buck. But because of the long-term nature of many cybersecurity risks, it also allows them to consider and model whether a big upfront investment in technology pays off and when. So for those two phases, you collect the range estimates outside of BayesiaLab and import them as hyperparameters, or you can manually enter them as node parameters in the interface, or you can manually define the distribution shape with the interface via shift-click, or you can use pkey. So clearly we have options when it comes to expert knowledge elicitation, but I don't think there are experts in cybersecurity, and my reasoning for that can be understood by reading the research by Kahneman, Klein, and the research by our keynote speaker, Dr. Sivani, especially in his book, You're About to Make a Terrible Mistake. And I'll publish a post in Hive Systems blog called There Are No Experts in Cybersecurity, where I'll explain my argument in more depth. But basically, I argue that cybersecurity has mostly low validity environments where few of us experience the kinds of cues and events needed to establish an intuition necessary to give accurate and informative estimates. But there are effective ways to reduce or correct for expert bias. In one way is to integrate the data you do have, even if it's sparse. So you can plot your data with your expert estimates and calculate the regression, something Dr. I think is going to be discussing tomorrow in more detail. And I'm very excited to see that new feature and approach. And I do hope to try it out in cybersecurity problems. Data, as we've seen, isn't hard to come by in cybersecurity. Computers tend to record everything. Your computer logs when people log in and out. It logs when you access or modify files. It logs, your router logs when you visit websites and when websites send their visual data back to your computer. Unfortunately, as the audience pointed out in the previous talk, hackers know exactly what data we have and how to avoid showing up in the data while they evade detection. So, well, in fact, stealing, modifying, and deleting data is their specialty. So in addition to the problems all research have with data, we have this active human intelligence also messing with our data and with great incentive for profit by doing so. One source of data we do have in cybersecurity is the Verizon Data Breach Investigations Report. And what goes into that is investigation data from across the globe. The people who investigate cybersecurity events at an organization have to journal their findings and case outcomes. So Verizon collects that data from multiple parties, enriches it with outside sources, and then finds patterns and then publishes this report for free. Well, you have to give them your contact information, of course. So they're still going off a convenience sample, and most companies don't want to disclose information that they would like. And I doubt the ones that do report information to them are entirely truthful about those disclosures, because liability comes with admitting and putting these things on paper when it comes to security. And what comes out of the Verizon analysis is usually a set of themes or patterns that they see across the data, basically variable clusters that give a summary, that they give summary stats on. It isn't great, but it's the least bad report available in our field. And given that most people are starting their risk assessments from scratch, that every time they do them, it would be nice to have a baseline to at least consider as part of our risk models. So what might be useful is a model of the cybersecurity risk universe according to Verizon. So kind of the data breach report as an expert at your table. And the data set behind the report is unfortunately not public. So you can really just use the summary statistics from the report. I entered those into BayesiaLab along with the sample sizes as prior weights. And on the left in yellow are the stats about investigations that ended in data breaches. And on the right in black are the stats about investigations in general, whether they're data breach or not. And at this point, I've been trying to simulate the structure of the Bayesian network and how these variables interact. And that's where things get tricky. I tried generating a large data set that fits these parameters and then tried to machine learn that structure, hoping there's enough co-occurrence to find those patterns. And unfortunately, even the lowest MDL machine learning ensemble gives you something like this. In retrospect, the statistics, I started with cover such broad areas that there's very little independence between them to define. And it's not because the ground truth isn't lacking in independence. It's just that the report variables chosen are all very dependent on each other. And just for fun, I tried the independence of causal influence routine with a lot of effects, or a lot of these effects did accurately correspond to where you would expect end users employees are responsible for the error-based breaches where you accidentally expose stuff to the internet. Sysadmins are responsible for the privilege misuse data breaches where you have like a disgruntled systems administrator causing a breach. But then every other node had at least one incorrect effect response. So it's a work in progress. And a portion of Verizon's data was based on a community sourced database called Veris. Companies that have security operations centers can journal their investigations using this Veris schema and contribute to the database. The features now go well beyond the basic security investigations, technical observables, and they include things like organization size, breach cost, whether company policies were followed, and so on. So I picked a few interesting variables, batched the learning algorithms to find the best fit. And the structure does make sense. BayesiaLab discovered the clusters and patterns quickly without knowing cybersecurity. And with parameter updating, your security operations center can keep updating a network like this as they go about their day-to-day investigations. And by doing so, they can get a reliable probability of whether or not an investigation is going to end in something juicy or not, or if they're just kind of spending, there's a high cost investigation. Investigations does seem feasible with Bayesian Networks and many of the features in BayesiaLab. And thanks for joining me. Hopefully you found it helpful. If this topic interests you, look for me at the next BayesiaLab conference. Look me up at hivesystems.io. If your area of expertise isn't cybersecurity, there's still a lot that I learned from everybody in these conferences, and to see how I can apply this to cybersecurity. And I hope that maybe you got some inspiration from this, from the different angle. Lastly, I'm a cybersecurity person and not a salesperson, so please don't hesitate to reach out if you want a second opinion on a security problem or idea. Thank you.